Whenever you're ready, go ahead.
Okay. Hi, my name is Laura Spiegel. This is Cameron Fry, and this is Alexis Rattle. We're from Belleville High School in Wisconsin, and our research project today is on differences in lunar sinuous rills across Mare basins. We completed this project with help from our teacher, Mrs. Treader, and our advisor, Gavin Tolometti.
Our studies are based on sinuous rills, which are meandering channels that are on the moon that resemble dry riverbeds on Earth. Most sinuous rills are found in Mare basins, which are remnants of lava plains, and they are also remains of ancient lunar volcanism. The study we have conducted is we have collected data from multiple sources to investigate variations in physical characteristics of lunar sinuous rills across 4 different Mare basins. The purpose of this research is to come to a broader understanding of lunar volcanism and how it affects formation of sinuous rills and consequently the lunar Maria formation.
So to start off with our data, we collected data from a study titled Lunar Sinuous Rills, Distribution, Characteristics, and Implication for Their Origin. We have data from 4 Mare basins, Procellarum, Imbrium, Serenitatis, and Orientale. I still don't know how to pronounce that. And we basically collected data on the length, the average width, average depth, and then average sinuosity. And sinuosity is the measure of like the bend or the windiness of a rill. And you find it by taking the length of the channel over the straight, over like the overall length, you divide it and you get the sinuosity index. And we found all the averages. And we also took ranges of the minimum and maximum values for each of the measurements at each of the basins. And then we have some tables down here to kind of visualize it. And on average, we found that Procellarum and Imbrium have longer, deeper rills with greater widths. Orientale and Serenitatis had shorter and narrower rills, but also higher sinuosity indexes. And so then for our analysis, we collected data from studies on terrestrial lava flows and tried to like apply it to sinuous rills on the moon. And we looked at 2 different variables, a fusion rate, which is the measure of lava's volume combined with its velocity, and then yield strength, which is the measure of how much force is required to get lava to flow. And we found that high fusion rates generally create longer lava flows. High yield strength makes deeper or wider lava flows. And so we kind of applied this then to these sinuous rills that we saw in the basins. And we concluded that Imbrium and Procellarum most likely their rills were formed with higher fusion rates, higher yield strengths, and Orientale and Serenitatis, their rills were most likely formed by smaller scale events with lower yield strengths and lower fusion rates. Also, wait, one last thing. So we also looked at 2 other variables, which were the estimated ages and the diameters of the basins that the sinuous rills were found in, to see if there was a correlation with that. And we found that the ages really had nothing to do with the physical characteristics of the rills. As you can see, Imbrium, Serenitatis, Orientale, they all have about the same age, and then they have vastly different characteristics. For the diameter, like how big the basins are, that's a little more difficult because on average, Imbrium and Procellarum, they're the biggest, and they have on average the longest and the widest rills. And then Orientale and Serenitatis are the smallest, and they have like the narrower, shorter rills. So at first, we were kind of thinking maybe how big the basin is has something to do with what the rills appear like. But it's important to note that the sizes of the basins, they mostly indicate the size of an eruption event. So larger eruption events have the potential to create longer, wider, and deeper rills. And then smaller events have the potential to make like narrower, shorter rills. but the physical characteristics of rills have more to do with the kind of eruptions that take place rather than how big the mare that they're found in are. They're correlated, but we didn't really find any causation.
So we then took the like information from the rills with the lunar flows and then put it to like the story of like the mare overall that like the rills were contained in. And we found that the Procellarum mare was likely formed by a larger scale event with high effusion rates and high yield strength material. Imbrium was likely formed under similar conditions of Procellarum, but with slightly higher yield strength due to like the on average thicker sinuous rills. Serenitatis likely formed through an event in smaller scale compared to like the previous two mare, and probably had a low effusion rate and yield strength, causing it to form like
2
on
minutes.
average shorter and thinner rills with a more sinuous structure. And Oriental likely formed under similar conditions to Serenitatis, but with higher yield strength due to like higher average depth of sinuous rills. And the rill comparisons, as you can see, Rima Sharp is an example of a very long rill found in Oceanus Procellarum with high effusion rates. Orientale rill is an example of a really short rill found in Mare Orientale, which shows low effusion rates. Vallis Scroteri is an example of a very deep and wide rill found in Oceanus Procellarum, which shows high yield strength. And the Procellarum rill is an example of a very thin rill found in Oceanus Procellarum, which shows low yield strength.
And after we collected all this data on physical characteristics of lunar rills, including variations in length, width, depth, and sinuosity, in order to cause what causes physical differences in rills across different mare basins, we found that on average, Procellarum and Imbrium have higher average lengths with steps, while Oriental and Serenitatis have shorter, narrow, and more sinuous rills. And in order to interpret these differences, we compiled research on properties of how lava
30
flows
seconds.
and rates, yield strength, and paths impact the eruption patterns of molten material. We then use this information to suggest that Procellarum and Imbrium were formed through large-scale abrupt events with high effusion rates and low yield strength. Oriental and Serenitatis were formed through slower events with lower effusion rates, and in the case of Serenitatis, lower yield strength. And for acknowledgements, we have a very special thanks to Aaron Schroeder, Gavin Tolometti, and Andrew Schrader for helping us with this project.
I think we're good.
Okay.
All right. Yeah, sorry. I meant to mute that back again. Okay. Anyway, very good. Thank you. Any questions from anybody, judges or anybody else listening in?
No, I just wanted to say I appreciated the color palette. I've never seen a scientific poster done in this color style, and I really liked it.
Thank you.
Thank you.
Yeah, thanks.
Yeah, and I noticed too that that you took some of the feedback that I gave you and you implemented it on the poster today. So I thought that was really nice to see.
Okay.
Yeah, I mean, I would also agree. It's nice to see that you responded to the comments and questions. And maybe just kind of like a general question. So across these basins, can you describe like how you envision maybe like how volcanism has occurred within a basin, a single basin as an example? Do you see it as like one focused like large scale event, or do you see it more as a series of events occurring over time?
So that's a good question. So with basins, like especially such as Procellarum, because like it's so big, there most likely were like, I guess, multiple events that happened over the course of, like with the basins with like thicker, longer rills, their events were likely a bit shorter and more intense. And then, so that's like Procellarum and Imbrium. But yeah, they likely had like multiple events, maybe with probably different like characteristics in the volcanism, like different effusion rates, different yield strengths, especially like with the ranges. Procellarum had like out of all of them, like the biggest ranges between like its smallest and its biggest rills, like its widest, its thinnest rills. And so I guess you could say that indicates that there were like different events going on that caused like different varieties of rills to form.
Yeah, thanks. Yeah, I definitely like personally from my own research have seen like that there's a great variety of volcanism across the moon in terms of like large scale events, small focused eruptions, and you get like lots of different lava texture and thicknesses. Some are like really thin, well, like maybe meters thick, and then others will be like tens of meters thick. And then some of the cool results that came out of LRO, for example, they found some areas where lava flow seemed to have like a really unusually rough texture, which suggests that it had a different eruption characteristic compared to like a more typical Maria. Yeah, so that's really cool that you're investigating all these different possibilities. Yeah, thanks.
My team was wondering, since we also did one on sinuous rills, I was just looking to see how you collected your data and where you got your data. I didn't see that unless I missed it. But where did you find most of your data?
So we found it was like a really good like scientific paper that was sent to us by our advisor, and it was a study done, I think, pretty recently. But it was called, I have the, oh yeah, show the references.
And which number it is.
It's not
very well, but
number 2. But it was called Lunar Sinuous Rills, Distribution, Characteristics, and Implications of Their Origin. And it was by, I think, Hurwitz, Head, and I can't read the other last name.
Hieslinger?
Yeah. But basically what they did is they, all the data was kind of like there. They had like a huge spreadsheet with every single rill that they documented with the length, the width, the depth, and the sinuosity. So we kind of took all that data and like compacted it into the averages and the ranges.
My team agrees. We liked Hurwitz's paper too.
Yeah.
And I think he's got the best one. You know, I mean, it was really good. We also found another one that was good. It's by, I think you pronounce it Poda or Pada, that kind of did like looked at his data too, and then found a few more and talked about it. So I think it must have inspired a few people to look at rills. So yeah, I agree. It was a very good paper. I mean, I'm not an expert, but it seemed like it's very good. All right. Well, thank you very much.
Thank you.
Yeah, thank you.
Okay, anybody else? Questions or comments?
I have a question for the team. Why do you think it's important to know about the different yield strengths of different basins?
I guess because like in one of the papers that we looked at, that was talking about like what causes like different characteristics of differentiation in lava flows, they mentioned yield strength. And so that's just kind of like one of the like explanations we took for like the differences. Yeah, I guess, yeah, it was just one of the factors that we found.
Thank you.
Okay, thank you, Belleville High School. All right.
Thank you so much.
Okay, up next is Crum High School.
Why is it not letting me stop sharing?
Are we good to start?
Yep, whenever you're ready.
Again, I'm Ella Sager.
I'm Mackenzie Manning. I'm Cadence Foshi.
This is our project, Lunar Habitation through the Use of Lava Tubes, Artemis' Next Frontier. This is our table of contents. We have introduction, methodology, Artemis, information, data collection, results, and conclusions. Our research questions are, where would the best locations be for establishing lunar lava tube bases as the Artemis missions progress? And what space companies could help accomplish this? Lunar lava tubes have been suggested to be used for habitation on the moon because they protect from radiation and the bombardment of micrometeorites. Lava tubes are tunnels formed by former lava flows that have been hollowed out. Lunar reels are simply collapsed lava tubes, but can be used to indicate lava tubes nearby, which is why reels are the basis of our research. Various space companies are already doing research on lava tubes, which aids in the mission to create lava tube habitation. This photo is an example of one of the lava tubes on Earth that are being researched because it has similar conditions to the lava tubes on the moon. This photo is a possible lava tube skylight located on the edge of a lunar reel, as many skylights are.
And the methodology, the sequence of research and data collection. Using LROC quick maps and JMRs, we gathered spreadsheets of data, specifically selected craters and reels that could potentially contain lava tubes to help further our research. Using the spreadsheets filled with the measurements such as height, width, and length has helped us eliminate these options. Through the use of NASA.gov, we went through many companies associated with NASA to discover their part in the lunar habitation projects. We gathered spreadsheets and focused on the companies most beneficial to our project, such as SpaceX, Blue Origin, and Fourth Planet Logistics.
Artemis is another big part of our projects. The Artemis Accords are rules which certain countries are planning to abide by, 23 countries plus one territory outside, excluding India, China, and Russia. China and Russia are working on International Lunar Research Station, the parallel to Artemis. Russia was at one point part of Artemis as well. The Artemis missions require many innovative solutions to get astronauts to the moon. One such is habitation, which is why the concept of lava tube bases is important, especially in Artemis 3. This is a photo of the 13 candidate Artemis 3 landing sites that are near the south pole of the moon, which is generated by NASA.
And our data collection. In the beginning of our research, we focused our attention to craters over 15 kilometers to help us potentially locate reels to begin our research on lava tubes. This chart shows craters that we chose in hopes that they could contain reels, which could serve as lava tube bases. The graph is a visual representation of the diameters of the craters in the chart. But after researching, we gathered majority of lunar reels in the southern Maria because the habitats for the Artemis missions would be close to Artemis 3 landing sites in the southernmost area of the moon. The chart shows some of the reels that could possibly indicate locations of lava tubes for these purposes. The chart shows the coordinates and length of each reel, and the graph next to it shows the height and width of each reel.
Was the second part of our project. Most companies are in America, Airbus, Defense, and Space being the most prominent international. On the graph, blue is the smaller companies that are partnered under the bigger ones. The magenta pink is the lunar lander partners, while the red is the human landing systems partners. And the green in this situation is Blue Origin and Northrop Grumman's fight for the moon lander contract with NASA. Boeing, Lockheed Martin, Blue Origin are major companies in air transportation other than spacecraft. Lockheed Martin is a leader in the Orion spacecraft, which is what NASA is planning to use for the future Artemis mission. United Space Structures and Fourth Planet Logistics are less known, but are actively looking into lava tubes. They're also looking into 3D printing and inflatable houses.
our results. The majority of lunar reels are located within the Maria, meaning the southernmost reels are a considerable distance from the Artemis 3 landing sites. However, that doesn't make the concept of lava tube bases useless. If the Artemis missions expand their research to other parts of the moon, lava tube habitats would still be a way to shelter astronauts in these areas. This image shows where some of the southernmost reels are found on the moon. Remae Janssen, the closest reel to the south pole of the moon, is about 1,200 kilometers away from the pole. This image shows the locations of the craters that were used to find potential areas for establishing lava tube habitats.
Spin Launch is not part of the working companies, but is working on energy efficient launch with kinetic energy. This is one of their inventions. This is a concept rendition from Fourth Plant Logistics of a lava tube habitat with 3D printing and trails. This is an artist rendition from United Space Structures, the surveyor of lava tubes, surveyor Cisluna Space Logistics. And finally, the Fourth Plant Logistics robot applying pressure barrier sealant to a lava tube wall. And this is all of it together.
And our conclusions.
This is the final 6 companies. The United Space Structure is surveying for habitable lava tubes using the surveyor Cisluna Space Logistics. And they're also making a lunar data center network. Fourth Plant Logistics is using pressurized terrestrial lava tubes by atmosphere
2 minutes.
as seen in the 4th image or the robot to be the primary or secondary structure shell. They're also looking at 3D printing structure and traveling paths, as well as inflatable habitat within the lava tube. Honeybee Robotics and Empower Technology are working on the Lunar Charging Station, which are the Dragon scales that are lightweight and flexible photovoltaics, and the Lunar Power Grid for Artemis exploration, the Lunar Array Mast and Power System lamps. This can be used at any base types. Spin Launch is solving the problem with space travel pollution with kinetic energy launch, which uses no fossil fuels, and coinciding with the Artemis Accords registration of space objects, which is the safe and sustainable environment for space. SpaceX has the most resources and money to contribute. With many contracts with NASA, the Starship was supposed to be used in Artemis 3, and they are also working on the Gateway. The Starship, quote, can carry up to 100 people on longer duration interplanetary flights, end quote. And it should be able to carry the building resources for the moon base.
More companies could dedicate their resources to the exploration of and research into lava tubes and their physical relation to lunar reels for the goal of expanding the confines of interplanetary habitation. Companies such as United Space Structures, Fourth Plant Logistics, Empower Technology, Spin Launch, Honeybee Robotics, and SpaceX could help in accomplishing the goal of creating
30 seconds.
Using lunar reels to find skylights that open up to intact lava tubes and establishing habitats in these tubes can pave the way for future Mars exploration and habitation as the Artemis missions continue through the decades.
Acknowledge our teacher.
And we acknowledge our teacher, Ms. Hardy, and our advisor, Dr. Z. And that's it.
Okay, thank you. Okay, any questions for Crum High School? Don't be shy.
So you mentioned that you used several large craters to basically determine where to then search for rills in those same areas. So did you find any link to like certain craters had a way more rills than you thought or less, or did you find any connection between the craters you were searching for and the rills that you studied?
We compared a bunch of craters located in the Maria, and then we compared them to ones located in the Highlands / South Pole area. And we noticed that there was a lot more rills in the Maria because that's where most of the lava flows were, compared to the South Pole where there isn't as many.
Thank you.
Hi. Can I ask, did you utilize any of the existing databases for lava tubes and skylights when you were assessing the different ones for potential habitation use?
We used JMARS to look at the Marius Hills, which has a potential skylight. So we looked at that.
Okay. There has been a couple of papers, which I can maybe send you a link to if you're still interested, that documents about a couple dozen different skylights and lava tube areas. And then just like a follow-up question on that, do you think we have found all of the lava tubes that have actual skylights or access at this point? Or I guess what's the rationale for needing to do more surveying versus, like, I think you mentioned one of the companies wants to survey for lava tubes. Do they have like a rationale for doing that?
We don't think that we found every lava tube because they can be hard to find, especially when scientists come upon skylights. They usually say potential skylights.
The surveyor is still in prototype stage or artist renditions, and there's not much information on the site about it. Just a general idea of this is what we're gonna do.
Okay, yeah, thanks. I think I hear what you're saying about so there's candidate skylights, but we don't really know what's not visible to us beneath the surface. Yeah. Cool, thanks.
Okay, anybody else? All right, great. Thank you, Crown High School. And last but certainly not least, Logos. So go ahead and share your screen and then start whenever you're ready.
Okay. Where is it?
Share screen. ExMASS.
Oh, you see nothing. All right. So we are students of Logos Public Charter School in Medford, Oregon. My name is Summer Johnson and I'm in the 8th grade.
My name is Kyle Klarstrom and I am in the 10th grade.
My name is Asa Nelson and I am in 7th grade. As you can see in the photo shown above, we are standing in the entrance to Valentine Cave at the Lava Beds National Monument. Our team went there to see features that we might see and compare to on the moon. We became interested in lava tubes and sinuous rills, which we found at the park along with pits and skylights. We read that lava tubes could one day provide shelter for humans on the moon. This is how we chose our topic, sinuous rills. The title of our project is 12 New Candidate Sinuous Rills on the Moon. Here's an example of a rill, Hadley Rill.
Lunar Asteroids are meandering channels of varying depths and widths with parallel striking and laterally continuous walls and are commonly found within the lunar mare. Their ages range between 3 to 3.8 billion years old. How do lava tubes and sinuous rills even form? There are different ways they can form. One way is by opening channels. The other is as described here. First, large basaltic lava flows carve out channels. Currents keep the core hot while the edges cool and thicken as they are exposed to the surface. The top of the flow crests over from the sides like the way ice freezes on a river. Second, the crust eventually joins completely at the top, insulating the interior and superheating the flow. Third, the superheated lava flow begins thermal erosion, and it starts down cutting through the ground or lava flows beneath it. This results in a deeper, narrow cross-section. Fourth, when the eruption stops, lava can drain from the tube, and that leaves behind the vacated conduit beneath the surface, which is a lava tube.
Here are examples of thermomechanical erosion and skylight formation in some of the lava tubes at Lava Beds National Monument.
The last step to form an SR is the thermomechanical erosion of flowing lava for subsurface lava tubes, causing their collapse after the lava drains out. This forms openings in lava tubes, forming sinuous rills and pits. The images here is a comparison of a sinuous rill on the moon and at Lava Beds National Monument, as well as pits.
Although this is not the focus of our study, SRs may indicate the location of sections of intact lava tubes, which could serve as sites for inhabitants to shelter from the harsh space environment during future human exploration of the moon. If a person wanted to explore the moon, it would need shelter from radiation, extreme temperature changes, and micrometeorites. Lava tubes might offer these, as well as housing astronauts and storing their supplies.
There are 200 known sinuous rills on the lunar near side and none documented on the far side yet. For human exploration on the lunar far side, sinuous rills and associated tubes could provide shelter and other resources. Our goal is to identify sinuous rills on the lunar far side with similar morphology of the ones documented on the near side. We will use morphological characteristics of known sinuous rills such as length, width, depth, slope, and sinuosity. For gathering our data, we used LROC, LOLA, and QuickMap measurement tools to get distance and height data. For length, we would trace each side of the rill. Then we would gather distance data. After that, we would add the two distances together and divide by 2. For width, we divided the rill into 15 to 20 evenly spaced segments, then estimated each edge of the rill from one side to the other for each segment, and then subtract the difference from the line distance. For depth, we again divide the rill into 15 to 20 evenly spaced segments, and for each segment, we find the terrain height on both sides of the rill and average them. Then we find the terrain height of the lowest point in the rill. The depth is the difference between the two heights. For slope, we create an area 3 times the average width of the rill, avoiding any major changes in elevation. Next, we gather the average elevation of said area and repeat the process on the other end of the rill. Then we find the difference between the two elevations, which is rise, and we measure the point-to-point distance between each end, which is the run. Finally, we calculate slope angle with the equation rise over run. For sinuosity, we divide the rill length by the straight line length, which is the distance from the start and end points of a rill in a straight line.
In the results, we identified 23 features as candidate SRs with an average of 23.7, with the shortest of 6.19 kilometers, longest of 92.53 kilometers, width was 1.16 kilometers, depth is 111.28 meters, sinuosity is 1.28, and the slope is minus 0.19 degrees. As stated before, our goal was to identify new SRs on the far side of the moon with similar morphology to those documented on the near side. In the following slides, it will be shown that our data from the candidate SRs exhibits similar characteristics to that which was gathered by 1 and 2. These characteristics include length, width, depth, slope, and sinuosity.
Length, width, and depth of the candidate SRs follow the same or similar trends to the known SRs. The test SRs are included to verify our methods, and they also fall in line with the known SRs. Our data set was roughly 30 rills in total, compared to the roughly 200 known SRs documented by Hurwitz and Poda.
For the slope and sinuosity, it can be seen that the candidate sinuous rills do not exactly match up with the known sinuous rills. However, they do follow similar distributions that are well within a reasonable margin of the known sinuous rills. The age distribution of the candidate sinuous rills shows a similar distribution to Hurwitz's documented rills, with the majority being between 3.7 and 3.8 billion, and Hurwitz's being between 3.0 and 3.8 billion. Our candidate sinuous rills compare well with the roughly 200 sinuous rills documented on the lunar near side in length, width, depth, sinuosity, and slope, and broadly formed during the same time span as those on the near side.
Out of the 23 features we found that fit this list of SR morphologies, 12 are candidates for SR classification, whereas 11 are labeled on the geologic lunar map on QuickMap as lineaments of unknown origin. The image shows a possible origin for the unknown lineaments is the result from tectonic uplift and or volcanic modification of the lava flooding a crater.
In conclusion, we mapped 23 new features with similar characteristics of SRs, whereby 8 candidate SRs are located on the far side of the moon, with 4 located on the near side.
30 seconds.
We propose that these 12 features should be considered as new SRs. 11 unknown lineaments also exhibit SR characteristics, possibly extending the total to 23 new SRs. Thank you for listening to our presentation. We hope you enjoyed it. We thank our mentors and for you allowing us to be a part of this. These are our citations and credits.
Great. Thank you, Logos School. Questions?
Do you guys have plans to follow up and submit some of these to the committee that would formally name these as sinuous rills?
Yeah,
we do.
Cool. You should definitely follow up. That's a great idea.
Can I ask a question too?
Yeah, go ahead.
Thanks. Do you have any thoughts on why maybe it's been harder to identify sinuous rills on the far side compared to the near side?
On the far side of the moon, there are less Mars and more craters, which can hide a lot of them. The craters could obliterate them too.
Cool, thank you.
Okay, any more?
I'll just say I also wanted to echo what Ruby said. That's really exciting that you found some new rills.
Yeah,
We enjoyed them
it
too.
was lots of fun finding them and going through data.
All right, so hi, I'm Adi Swaminathan, and I'm a junior at Tenafly High School, and I'll be presenting today about using linear regression of mineral abundances from moon craters to yield insights into the magma composition. So first, I'll introduce our team. So our co-authors were Anjali Jatavedam, Derek Cho, Serene Jang, and Casey Yam, and they helped me extensively with the data collection. Without them, this project would not be in existence. Our advisor, the late Dr. Coyle, gave impetus to this project when it stalled, and she helped us coordinate, meet deadlines, and keep the project going. And she gave this project the momentum it needed to get where it is today. And so our mentor is Dr. Jeff Plesha from the Johns Hopkins University Applied Physics Lab in the University of Maryland. He was immensely helpful in giving this project direction, showing us a source of data, teaching us about the moon to inform our research, and showing us the capabilities of the Lunar QuickMap platform, which is where we got our data from. He gave us crucial advice at critical junctures, and he helped us explain some of the correlations we came across, and we're extremely grateful for his mentorship. So now I'll actually introduce the project itself. So the objective of the project was to examine the mineralogy of the different units of impact craters on the moon, specifically the crater interior and the surrounding ejecta, and to understand the differences and the similarities between the Maria and the Highlands composition and the variations of the mineralogy. And so the minerals we studied as part of this were, we looked at the orthopyroxene abundance, the olivine abundance, the plagioclase abundance, the iron abundance, the iron oxide abundance, the clinopyroxene abundance, and the titanium abundance. And so now I'll explain our methodology. So as I said, we collected data using the LRAW Quick Map platform. So what we did was we used the line profile tool and captured one diameter extending from the ejecta through the wall and the interior, and then out to the ejecta on the other side for every profile. And on the left, you can see how we have multiple profiles, which are the different diameters. And so in such a manner, we collected 5 diameters from 18 craters whose diameters were longer than 10 kilometers. And on the right-hand side, you can see we can add parameters for which we wanted to download data. So you can see on the right here, you can see iron abundance, orthopyroxene abundance, etc. And so, yeah, so there's a download button that you can click, and that gives you a table of 700 data points across the line profile. And so we had initially planned on taking data only from 1 diameter for each crater, but then based on Dr. Plesha's advice, we decided to take data from multiple diameters from each crater. That way we could better capture the variation inside each crater. And so because of that change in plans, we also had 5 single diameters from craters of diameter smaller than 5 kilometers, which is from the previous stage of the data collection process, which is before we changed the plans. And we also included that in our analyses. So LRAW Quick Map only let us download data for each mineral individually, and so we ended up with separate tables and separate files for each mineral. So as you can see here, shown are 2 separate tables, each with data on a different mineral from the same diameter. And so to be of better use, we needed to combine these into one table. And so for this, we made a Python script. So just a quick explanation of how the script works. In lines 4 through 6 here, what those lines do is it imports all the table files into one list of files. And then the final lines of the code here go through the list of files and add the column of data that has the mineral abundances to the final table. And then lastly, it saves that table to a file. And so running that Python script produced a file with a combined table with all of the data from 1 diameter. And so we repeated this for each diameter and then put together all the single diameter tables. And so what's shown here actually is a single diameter table, meaning it has all the various data points for 1 diameter. And then we took all of these tables and then we put them together into 4 larger spreadsheets. One with all the data from all the diameters together, and then one with all the data for craters of diameter shorter than 5 kilometers, one with data for craters of diameter between 10 and 50 kilometers, and then one for the diameters greater than 50 kilometers. So this way we can analyze the size categories separately, but then also all together, so we can see how they perform individually, but then also together. And so the next task was to perform the actual graphing in the regression. And so for this, we use another Python script. So this is a slightly longer Python script. So I've broken it down into 3 parts. So in this first part here, lines 1 through 10 make available for use all the modules, which are the sets of I'm not sure how familiar you are with coding, but essentially, there's things called modules, which are sets of pre-coded functions that can allow us to perform a specific set of tasks. So in this case, that would be graphing and doing regression. So as you can see here, these import statements at the top, those tell the compiler to grab those sets of code and make them ready for use in my program. And so lines 11 through 22 here set up the graphing and create the lists of the variables to be graphed. And so you can see here the list of iron abundance, orthopyroxene abundance, etc. And you can see here how there's separate markers for the circular data points, for the Maria data points, and the triangle data points for the highlands. So that's set up here. Next, the for loops here at the top essentially tell the code to loop through all the various lists and to graph the various combinations of data points and parameters. So that would loop through every combination of y variable and x variable and every diameter length range, etc. And then lines 35 through 38 here set up a list of colors, which then allow me to graph the data points from each diameter in a separate color. So that's the color coding you would have seen in the graphs from the poster. And so lines 43 to 54 here select the data that we want to graph, and then graph it, and then perform the regression on the relevant data points.
30 seconds.
And so the code here is actually only for data from the Maria, and then it's repeated for the Highlands, and then for both together. And then so lastly, these last few lines of code set up the axes titles, the figure size, and then save the figure. And then so what did the graphing and the regression produce? So the strongest correlations occurred because the two minerals being compared are highly characteristic of the Maria or the Highlands. So now we'll take a look at a few examples. So as you can see here, there's a very strong anti-correlation between iron oxide abundance and plagioclase abundance. And this can be explained by the fact that plagioclase is characteristic of lunar highlands rocks, whereas iron oxide is more characteristic of the lunar Maria. And so each data point samples approximately the same amount of area from the moon, which translates to the same amount of total matter analyzed in each data point. And so the total matter would be equal to the matter characteristic of the Maria plus the matter characteristic of the Highlands plus everything else. And assuming the amount of miscellaneous material that everything else, assuming that averages out, we would get this linear relationship between the matter characteristic of the Maria and the matter characteristic of the Highlands. And so we can also see this pattern occur with many of the other minerals characteristic of the Maria, for example, the pyroxenes, iron and titanium. And we can see how these produce strong anti-correlations with plagioclase, which is characteristic of the Highlands. And so by similar logic, strong correlations were also produced when materials characteristic of the Maria were plotted against each other. And the more Maria material the data sample enclosed, the more the minerals being compared were present. And so clinopyroxene, iron oxide, orthopyroxene, iron, and titanium are all characteristic of the lunar Maria. And here you can see some relatively strong positive correlations between them. So interestingly, there were no strong correlations between two materials both characteristic of the Highlands. So why does this occur? An explanation for this is that the magma which formed the Highlands was less well mixed with a more heterogeneous composition. So having more material from the Highlands present in the sample does not necessarily translate to having more of the specific mineral, even though that specific mineral may theoretically be characteristic of the Highlands. And this would explain why no strong correlations between two materials characteristic of the Highlands occurred. Furthermore, one explanation for why the magma may have been more heterogeneous is that the magma which formed the Highlands was more viscous, which would have hindered the mixing process. And on the other hand, if we look at the Maria, while strong correlations were present there because the lava which formed the Maria was more well mixed with a more uniform, more homogeneous composition. And so when there was more Maria material in the sample, there was more of every individual mineral which composed it, which explains the existence of the strong inter-Maria correlations as well as the strong Maria mineral versus plagioclase correlations. And so again, an explanation for why the lava was more homogeneous was that the lava was less viscous, which should have been conducive toward the natural mixing process. And so, in fact, doctors Jerome A. Neufeld and Chloe Michaud write in their paper, which explains the formation of the lunar primary crust from a long-lived slushy magma ocean, that at the surface of the moon, cooling drives enhanced solidification and the development of a very viscous and stagnant lid. And so our explanation for why there were no strong correlations between Highlands mineral abundances is supported and actually supports a paper published in the Geophysical Research Letters Journal. However, there still remains work to be done in our study because there was actually only one pair of minerals which we studied that was characteristic of the Highlands, and that pair was between plagioclase and olivine. So it may have just been a specificity of that pair that led us to that conclusion. So in order to strengthen the statement that there are no strong correlations between two Highlands minerals, other Highlands materials should also be collected, and then the same regression can be performed on those pairwise combinations. This way, our statement could be more strongly backed up with more Highlands minerals being studied. Yet, the result of the study is extremely exciting because it carries significant implications and insights into the composition of the magma and the formational processes of the moon. So a great thanks to the entire team, to the co-authors, to Dr. Plesha and Dr. Coyle for helping this project greatly. I would also like to thank you judges profusely, not only for your time, but also for helping us think deeper about the results. And the stimulation that your feedback provided actually continues to drive my thought. In fact, I found the paper that I referenced to support my explanation just last night while preparing this presentation. And I was even thinking about this project last night while I was asleep. And because the first thought that struck me this morning was that we had only one pair of minerals from the Highlands. So actually, like the major flaw in our study, I actually was thinking about it like while I was asleep. So I really appreciate your judges, you guys' time, your time for listening and your effort in giving me the very stimulating feedback. So thank you so much. So any questions?
Okay, thank you. Just an FYI, total was about 13 minutes.
Yeah.
No big deal.
I tried to speak faster.
No worries. No worries. All right, Julie.
Yeah, very cool. There was a lot of info in there. Just to make sure I'm on the same page, which were the two minerals that you're saying were in the Highlands that you didn't see any correlations with them?
Plagioclase and olivine. So those two didn't have strong correlation between them. And so when we stated that there were no strong correlations between two minerals in the Highlands, we were really only talking about just those two minerals, like between those two minerals. So a way I plan to extend this research is now I'm going to go and figure out which other minerals that we didn't look at are also from the Highlands. And then now I'm going to go back and do the same thing and see what I find.
Okay, yeah. Thanks for explaining that. Yeah, I don't know if I have any questions exactly, but just maybe some like more feedback on what you might find useful. So my background's in geology, so I would have naturally approached this from maybe the framework of geology, rather than maybe like physics or some other direction. But basically, so I would start with like the idea that each mineral is made up of different elements, and you have their chemical formulas listed there, so you can tell which elements are in each one, and then each one has a different abundance of specific elements. And then a rock is made up of mixtures of those different minerals, and so depending on the abundance of each mineral within a rock type, you might see different abundances of different elements. And so that's part of the reason why you see a difference so strongly between, like, I think you know this, between Highlands and Maria, is because they're made up of very different mineral mixtures in the rocks. In particular, like Highlands very low in iron, Maria lots of iron. And then the other thing though, that's just like a little caveat on this is that since you're relying on visible near infrared spectral information, some of the elements and minerals show up more strongly in those spectra than others, and they can actually mask other minerals that might be present because they are just so much more responsive in that wavelength. So for example, like where you see plagioclase, it really only shows up and you can detect it in that spectral wavelength because there aren't any other minerals present. It's like really only shows up when you have lots of plage and not much of anything else. But the reverse, where you have like a lot of like say pyroxene and some plage, it's really hard to pull out the plagioclase because the pyroxene is so dominant in the spectral features. So just kind of keep that in mind that it's not necessarily a one-to-one in all cases, and that can kind of mess up some of the correlations that you might be seeing.
Right. Okay. Yeah. So I guess some of the anti-correlations then, like I guess between iron oxide and plagioclase, so you're saying it's more due to the fact that when there was more of the other stuff, you just couldn't see the plagioclase, but
Yeah,
so
yeah,
it
it's especially
showed up.
true for
Okay.
like olivine too. Like it has to be like 90% olivine for olivine to show up in the spectral features very well. So yeah, spectral mixtures of spectral mixtures of minerals and Vis-near spectra are very hard to pull apart sometimes. So unless there's very end member compositions.
Yeah, and I actually, so this study was very like experimental and like exploratory for me because like so like this is actually my first like research project. So I actually just approached this from a very statistical point of view because I was like taking AP statistics, and we had in fact at that point in the year we just learned about linear regression. And so I was actually very excited to put that into practice. So when, you know, Dr. Plesher, our mentor showed us, you know, this troves of data, I was like, wow, I can, you know, do linear regression with this. And then I just saw, where did that lead me? And so that
Yeah.
was sort of the lens, I guess, which I approached the project through.
Yeah. Yeah, and I can tell that you're very interested and that you put a lot of thought into it. So that's fantastic.
Thanks.